So I'm really happy that we have Hong Gay here today, and I'll explain a bit why we invited Hong. So Hong has a background not in PL per se primarily, but he's coming out of a machine learning lab in Cambridge. He did his PhD with Zubin Garmani, so he's very well steeped in the machine learning side of probabilistic programming, and he's probably best known for leading the development of the Turing probabilistic programming language. And something that I'm excited about is to sort of connect the applied machine learning side of probabilistic programming more to the programming languages side. And I'm really hoping that our communities start talking to each other a bit more and learning from each other. And I really feel like we as programming languages people have technical skills and theoretical methods to contribute to the applications, and we also very much need to listen to the needs of practitioners and the inference experts. And I really feel like we can learn a lot from each other. So my hope is that by having really strong representation of the machine learning side of probabilistic programming here, we can sort of strengthen the connection between our communities. So thanks very much for speaking to us today, Hong. And,
right.
It's going to win this. Good. Take it away.
Okay, thanks a lot for the invitation, and thanks a lot for the kind introduction. I'm not sure I'm a strong representation from the machine learning side, but I will try to give my personal perspective on the topic. So here's my outline. First, I will give a general introduction to probabilistic programming and how we can use that to automate Bayesian inference. Second, I will talk a bit about the MSMC workflow in the Turing probabilistic programming language system. I will focus on MSMC in this talk, but Turing does support version inference and others. Then I will conclude on some lessons and challenges we've learned while developing Turing and the related libraries. As you already have learned, my background is mostly from machine learning side, so my knowledge about programming language should be taken with a grain of salt. Right, let's get started. Why we care about the Bayesian inference? Because we need to capture and propagate uncertainty in many scientific domains and also in real-world applications. For example, in the decision making, we do need to associate different scenarios with a sense of probability to be able to make rational decisions. And in science, in many important problems, we do need to quantify uncertainty. In machine learning, we care a lot about the regularizing models to control overfitting, and Bayesian is one of the very principled ways of doing this. Why probabilistic programming will help Bayesian inference? Because we need abstraction between modeling and inference. Abstraction is a very powerful principle that machine learning can learn from computer science. Right. A bit history about probabilistic programming. It's not a new concept. So the first popular probabilistic programming system is probably Winbugs. It got started in late 1980s. Then the initial release was made in 1997. This was developed in Cambridge at the MRC Biostats. David Spiegelhalter led this project, and Andrew Thomas was one of the main developers. Then there are many re-implementations of, several re-implementations of the original Bugs language. JAX, just another GIP sampler, is one of the popular ones. Then later, the idea got re-implemented again and again with different inference algorithms, with different modeling languages in consideration. Actually, the concept of probabilistic programming is very recent. Back then, there was no one referring to this software as a probabilistic programming language. It's just a software to automate inference or automate MSMC. At Microsoft Research in Cambridge, several researchers, including Tom Minka and John Wynn, they developed a software called info.net. This is mainly to automate message passing algorithms, including expectation propagation and also variational message passing. Then around 2010, a few researchers at MIT came up with this church paper. It's a sort of a language for generating models. And it got adopted by many people. Many variants are implemented to support different inference algorithms and to support different modeling families. In the Python world, we have PyMC, which was initially released around 2013. I think the history probably goes back further, and it is still under very active development. Then for sequential Monte Carlo and particle MSMC, we have two very well-designed systems. One is LAFI, and it sort of later got replaced by Birch. You probably all know Stan. This is arguably one of the most widely used probabilistic programming system. Some of you have worked on this. Then Turing was sort of first released around 2018, and as a sort of product to automate inference for some of our own models in Bayesian non-parametrics. There are many other systems like Pyro, NumPyro, another one in the Python world. The list will go on. It's hard to exhaust all the options. That's a great thing. Then I'll just briefly introduce a sort of different approaches to probabilistic programming. Sort of informally speaking, we can categorize probabilistic programming languages into three categories. The first category is graph-based. By that, the user will directly specify a graph, either using some graphical interface or using a modeling language. So this is the approach taken by the Box language and also taken by info.net. Box actually provide both. It provides you a modeling language. You can write your probabilistic graphic models using their language, or you can just draw it using their graphical interface. And the graphical interface actually predates the Box language. Second category is about simulation-based probabilistic programming systems. This is the most general approach to probabilistic programming because anything you can write a simulator, you can do it in this probabilistic programming language category. It's popularized by the church paper. It supports likelihood-free inference like approximate Bayesian computation, like importance sampling. And this is very convenient when the log density is intractable. By that I mean you can only write a sampling algorithm for your model, but not computing the log likelihood or the posterior. Then the third approach is about specifying a target function or a density function, often in the form of a log density. This is the approach taken by Stan, PyMC, Turing, and many other systems. In this approach, user directly implement the log density of the posterior. Then the probabilistic programming system will automatically compute, say, the gradients and many other sort of functionals that can be automatically derived from the target. Then HMC or variational methods are used for automated inference. I should mention this is not a formal categorization of probabilistic programming systems. Many probabilistic programming languages are a mixture of these three different approaches. Now, some differences between probabilistic and traditional programming languages. In probabilistic programming languages, there's a very close coupling between PPL design, the syntax design, and the runtime library. The runtime library refers to, say, the probability distribution functions, bijective transforms that will handle domain constraints in random variables, and most importantly, inference engines. If you look at some of the popular probabilistic programming languages like Stan and Box, they primarily support one inference algorithm. So Stan supports gradient-based inference, Hamiltonian Monte Carlo. Box supports gap sampling. And this choice of inference algorithm almost determined sort of the syntax design for the probabilistic programming language. So there is a very close coupling between the syntax design and the choice of inference algorithm. Then some other differences in probabilistic programming language. Often we need to generate many different evaluation modes for the same model. So if you implement a probabilistic model using the bug syntax, then I should be able to evaluate, say, the random function for the model. I should be able to sample from the prior. I should be able to evaluate the log density of the model. I should be able to compute the gradient of the model, and the list can go on and on. So it is about the idea you write your model once using the syntax, then the compiler will generate many different evaluation modes for the same model, and this is required by different inference algorithms. It is often desirable to extract the graphical structure in probabilistic programming languages. The graphical structure encodes the conditionally independent structure of the underlying statistic model. Knowing that is actually very valuable for improving efficiency of inference. For instance, this is utilized in message passing and gap sampling algorithm. Another distinction is we often want to extract the properties of model parameters. So for instance, whether a variable is a data is observed or it's a random variable. Some random variables are generated quantities, means they have no influence on the model. They are just the predictions the user want to use for downstream applications. Second property about model parameters is about domain constraints. For example, whether my random variable should be positive or should live in the interval between two endpoints. Another property is the dimensionality of my random variables, like the shape and size of my tensor. Some more differences. Building statistic models is actually intrinsically interactive and incremental. This might be actually a big difference between probabilistic programming and other programming languages. You might have heard this famous quote, all models are wrong, some are useful. So you can never come up with the correct model and then start implementing it. You often start from some naive model and then try to improve it. And that improvement process is incremental. You come up with a model, you fit it to some data, and then you evaluate that inference result, and then you see how you can improve the model. Another thing that makes probabilistic programming different is it has to be transparent to our inference algorithms. So the inference engines need to know what is inside the model. The inference algorithm has to look beyond the return value of your probabilistic model. You need to know the entire execution trace of a model. You need to know the dimensionality of the model. And the dimensionality might depend on control flow. So the inference algorithm also need to handle that. Sometimes advanced control of model evaluation is also needed. For example, when we implement particle filtering or particle MCMC for probabilistic programs, we might need to fork the execution of a probabilistic program, and that is not necessarily easy. So from that, here are a few elements for a powerful probabilistic programming language. We need interoperability. This is because the modeling library can actually evolve when we come up with new modeling families like Gaussian processes, differential equations. It is very hard to actually anticipate all these numerical libraries when you design the language. It's just better to open the language to the user to allow them to add new modeling families sort of as they need. The second is interactive workflow. This refers both modeling and inference. You sort of need to actually give a very intuitive, interactive workflow to the user so they can quickly check the model. They should be able to sample from the prior. They should be able to quickly evaluate the log density of a particular parameter configuration. They should be able to run MCMC sort of interactively for one iteration, see whether they get a high rejection rate. This list will go on. And then the final element is that we really need to co-design the probabilistic programming language with inference algorithm. And we are sort of in a good stage of this research area because there are already several very powerful, very mature probabilistic programming languages implemented. So we can look at some successful abstractions and then try to come up with better abstractions that can capture more inference algorithm requirements. So for example, now we can try to combine both the Gibbs sampling algorithm and Hamilton Monte Carlo. Try to sort of combine the ideas behind the box language and the Stan language to support a sort of more efficient inference. So that concludes my first part. In the second part, I will look at the Turing.jl ecosystem. This is sort of a probabilistic programming language embedded in the Julia language. Some of you might have used the Julia language. If you haven't, you should probably give it a try. I will start with some practical challenges facing MCMC algorithm. MCMC, I should say MCMC refer to Markov chain Monte Carlo. This family of algorithm is often hard to implement correctly because debugging them is not necessarily easy. Even you have a subtle bug in your algorithm, often you get very sensible results. It might take several years until you realize you have a bug in your implementation. There are many choices of MCMC algorithms. This is like a very wide range of algorithms. If you want to do fair comparison between different algorithms, it's time consuming. It's just not easy to implement one, let alone implementing many. Then another thing is in statistics and in machine learning, people often implement MCMC for a model. That means the algorithm and the model is not decoupled. That sort of limits the reusability of the algorithms or the implementations. And that's what probabilistic programming can help with. Probabilistic programming will decouple MCMC implementation from models. It will allow us to automate MCMC workflow. By MCMC workflow, I mean a bunch of things. Here is like an informal split of these things. The first step is about specifying your model using a probabilistic programming language or domain-specific language. Second, you should be able to condition on data. This is about feeding the observations into the model. Some PBLs actually hard-code this conditional step, but in Turing, we actually support the user to do this as part of their workflow. The third step is about performing inference using MCMC. You can pick your favorite MCMC algorithm. After that, you look at the MCMC chains. You see whether they have converged, whether you should have run them longer or run a different MCMC algorithm. Once you are reasonably sure your inference is correct, you can compute predictions. This is known as generated quantities in the Stan world. And this terminology seems getting more popular beyond the Stan universe. The final step, not the final step, but this interleave with the other steps. You should be able to perform prior and posterior predictive checks on your model to just see whether your model is sensible for the task you are trying to solve. Here is my favorite probabilistic programming demo implemented in Turing. The first line will load. I apologize for the small font. I will come back to this, actually. I will go through this step by step. The first line will just load some Julia libraries. Then from line 3 to line 6, this defines a simple multinomial model with a directly prior on the multinomial parameters. Then I will simulate data from this model by fixing my parameter p to a specific value. Then I will condition my model on simulated data and perform inference using Hamilton Monte Carlo. Then the last step, I will check whether my inference algorithm match the ground truth parameter. Why I like this model? Because this nicely illustrates the entire MCMC workflow. It's only 13 lines of code, but somehow it demonstrates all the important steps in Bayesian workflow and in MCMC workflow. Now let's dive. The first step is about specifying the model. I mentioned some of the elements. The first 2 lines, you don't need to worry. They are just loading some Julia libraries, very similar to import in Python or in R. Then from line 4 to line 7, sort of the model micro in Julia words, the at symbol will say this is a sort of a micro definition. The model micro annotate a standard Julia function. You can write whatever Julia support inside this model block. That's what makes the Turing language interoperable with the entire Julia ecosystem. And in this example, I only have 2 very simple statements. Both are stochastic statements. In the first one, I say I have a parameter p. It follows a Dirichlet distribution. And I have some hyperparameters for the Dirichlet prior. And then the second statement say I have a variable x. It's sampled from a multinomial distribution with parameter p. Is that clear? Feel free to interrupt if you have questions. Then after specifying the model, we in Bayesian workflow, we often want to see what the model encode by a sample from the prior. This is a simple but very powerful procedure for understanding inductive bias in the model and in the prior. And this is fairly straightforward in Turing. You essentially just run the model. You call the run function on the model. I should say the previous slide, this defines a model constructor. So if you call the function multinomial example, it will create a model for you. And then you call the run function on the resulting model instance. As you can see, the output is a name tuple of 2 variables, p and x. And these variables are sampled from prior. You can wrap inside a loop. You can run this step many times. You get sort of a chain from the prior. Here, a chain is actually not a Markov chain, but independent Monte Carlo samples. Now, let's make this slightly more interesting and more useful. When you have a model, you often want to condition on data. That is why we want to do all these things. And in Turing, condition on data is actually sort of part of the interactive workflow. You can use sort of the vertical line notation to condition on data. This is similar to the tilde notation. This is just trying to make the syntax very similar to the statistical notation. In the statistical world, you use the vertical bar to indicate conditioning. Right. Once we have created a conditioned model instance, I can run the run function again. And in this case, the parameter p is fixed to a particular value. So when you sample from the prior, you no longer get different values. You only get different values for the variable x. Then the vertical bar is like only a syntax sugar. Formally, it is equivalent with calling the condition function. The first argument to the condition function is the model, and the second argument is the parameters you want to condition on. You can also decondition variables from a conditional model. This is very useful actually during MCMC and also during model checking. So you simply call the decondition function on conditional model, then you get back to a deconditional model, which is sort of the model you defined at the beginning. You can also decondition only specific variables, a subset of variables you have previously conditioned on. Now, putting things together, I'm only copying the code blocks from my previous slides. First, we define a model. in this slide, I added sort of one extra line, a return statement. I will explain why this is interesting in my next slide. Now, with this model, I will first simulate some fake data from the prior. That's what line 8 is about. You essentially condition the model on a specific value for p, and this will sample a bunch of x variables. Then you condition the model on the sampled x to create sort of a fake posterior. Now you sample from this fake posterior using the Nazi algorithm for 1,000 steps. So this implement a full Bayesian workflow. Now you can look at the returned chain, and this is just looking at some statistics of the resulting chain. In this example, we are only doing inference for the parameter p because x is treated as data. So you can see in the summary statistic, you get p1, p2, and p3. You get the mean, standard deviation, Monte Carlo standard error, several variants of effective sample size, and also the R-hat statistic. You get a lot more, actually, and this is only showing a subset of the statistics available. You can also plot the chain. If you only just call the plot function on a returned chain object, you get a set of default plots. The first column are the trace plots, then the second column are the kernel density estimation for each individual parameters. You can customize this as well. There are many more other plots available. Now, the final step, we want to check whether our MCMC algorithm do the correct thing. So let's just compare the inferred parameters p against the ground truth. Now, remember, we simulated some fake data by fixing the parameter p to a particular value. That's shown on the line 1. So the p is a vector of 0.1, 0.3, and 0.6. This will sum to 1 because it is the parameter feeding into a multinomial distribution. Now, if we just look at the samples in the chain and plot the histogram, you can get the sort of the kernel density estimation. Similar, but here is a histogram for each element of p, and it roughly actually match the ground truth. When you collect more samples or when you condition more data, this uncertainty will gradually shrink and will convert to sort of a delta point, which is the ground truth. Now, this all look good. The final step is about generated quantities. I mentioned I will come back to this. The final line on line 4, I computed a very dummy expression for my parameter p. You can do anything here. This allows you to make predictions. If you do that, then after inference, you can call the generated quantities function with the first argument the model definition, then the second argument sort of a return chain. Then you get a new chain, which are essentially the predictions. And in this example, each row in my matrix is essentially a sample for p plus 1. You can see all these values are greater than 1. All right, any questions? Right. I mentioned that at the beginning of the second part, the reason we want to do purpose programming for MCMC workflow is we want to decouple model specification from MCMC algorithms. That means for the same model definition, I can easily try a different MCMC algorithm without changing the model definition. And here is just a subset of MCMC algorithm available in Turing. You have a random walk image, you have particle MCMC, you have a HMC, several variants of HMC. It is also very easy to sort of combine your own MCMC algorithm on Turing. Turing support a standard interface that allow you to use whatever MCMC algorithm you have available. Not necessarily in Julia world. You can also take your sample from R or Python. So for multi-threading and distributed computing, it's also very easy. You don't need to change your model. You don't even need to change your inference algorithm. You only pass a new argument to the sample function. It's either MCMC threads or MCMC distributed. Then it will run multiple chains in parallel, either on the same computer or on multiple computers. Now, a case study. So the previous example was nice, illustrative, but it's only on a very simple example. So in this case study, I'm showing a real-world model that's used by the UK government during the pandemic. So this is a spatial temporal model for COVID prediction. So it's collaborative effort of many research groups from Oxford, from Cambridge, from Alan Turing Institute, also from the Royal Statistical Society. And this is sort of a summary paper published at Statistical Science about some lessons we've learned while building these models. As you might anticipate, during the pandemic, time is actually very important. Quite often you need to implement your model and get the inference results quickly within a few days. That means you have to sort of decompose a big model, a big complex model, and allow people to combine them flexibly. And that is what this interoperability of statistical models is about. You want to essentially come up with a concept like functions, but for models. We call it submodels, but this is only early stage for that. So the main model looks like this. As you can notice, there are a couple of big blocks. I'm not going to explain this model in details. This is just to give you a flavor of the structure of the model. Now, does this work? So here is like a quick video of the predictions for the reproduction rate across the UK. This is a spatial temporal model. That means you can actually make different predictions for different regions in the UK across time. And this is very useful for more specific lockdowns. You don't want to lock down the entire country just because there are more cases in London. A bit more background on this model. This model was implemented in several PPLs. It's implemented in Turing. It's also implemented in Stan. So what motivated us to do several implementations? The Stan implementation works. It took a bit of effort to actually make inference work properly. But once that's done, it's done. The issue is the inference efficiency. Stan is sort of a language on its own. That means certain things are much harder to do than in a more general purpose language like Python or Julia. To run this model for the entire UK, it takes 20 days in Stan to collect 2,000 samples. That's clearly infeasible. You can't wait for 3 weeks to get one update. After re-implementing this in Julia, I should mention this is not really a strength or a property of the Turing language. It's more about the strengths we inherited from interoperability. We are able to implement the model utilizing more advanced features from Julia. There are certain convolution operators that we can do. We can also do some more optimization about the autodiff. And in the end, we reduced the inference time down to 20 hours. And that makes things a lot more manageable. And with that, we can quickly develop several different variants of the same model that allow us to test the different hypotheses. In fact, on this plot, we have 3 different models. So each of the map is showing the prediction for one different model. And each different model might look at different data sets. Now, coming back. So here, actually the model itself is not so big in terms of lines of code. The first block is actually the high-level definition of the model. I mentioned some model on my previous slide. You essentially decompose the entire model into 3 components. The first component is a spatial temporal GP. It is using Gaussian process as a prior. Second component is about sort of regional flux that's trying to use mobility data from region to region to improve the prediction. Then the third component is a likelihood model. Because we have many, many different data sets collected during the pandemic, so it is often very desirable to quickly try a different data set. And I'm showing one example for the 3 blocks. The spatial temporal GP is sort of listed at the second block. It's not big. The entire model implementation is probably around 200 lines of code. So that concludes my second part. Any questions here? Sure.
How did you do in practice afterwards? How did the predictions match reality?
It's working reasonably well. It's sort of consistent with some models, but slightly inconsistent with other models. But the useful thing is that this allows sort of pandemic researchers to try different hypotheses, and they will make their own predictions. We are not trying to tell them which model is better. We are trying to support them. Any other questions?
I need to say, is there a difference between the interfaces available on the model objects and the submodel objects?
At the moment, they are essentially the same. The syntax submodel, it can actually go away. Essentially, I mentioned some models are like functions. So when you call a function in your programming language, you don't call that a subfunction. You just call it, this is something I think a programming language community can probably help us to improve. Any other questions? Right, okay. Finally, just some quick lessons that we've learned during implementing these PPLs. So I sort of helped implementing 2 PPLs. The first one is the dynamic PPL. This is like a sub library for the Turing language. This is the DSL part for the Turing language. To give a bit more background, Turing is organized as many independent but interconnected libraries. The modeling specific language is in its own package called dynamic PPL. Then all the other MSMC libraries are in their packages as well. So that means you don't have to use Turing if you want. You can still use, for example, the NAS algorithm from Turing, or you can use the GP library from Turing. It's all very modular. So for dynamic PPL, the core idea is actually to utilize metaprogramming from Julia to implement a very user-friendly modeling syntax. The entire dynamic PPL library is essentially implementing the model macro and also all the functionalities you can perform on the model instance. It's not a huge library. We want to implement the principle. You write the model once, then let the compiler to generate many different evaluation modes. I mentioned some of these in the first part. For example, you should be able to sample from the prior using RAND. You should be able to evaluate the log density. In more elaborate cases, you want to maybe generate Gibbs conditionals. Or retrieve the marker blanket for a certain variable. Not all things are implemented in dynamic PPL, but these are sort of items on the wish list. Then another key idea is we we want high performance, and to get high performance, you need in Julia you need this notion of type stability, because the user doesn't specify types for the model parameters when writing the model. That means that the compiler has to figure that out. The way we do this is we will run the model once, then we collect a trace for the model, and from that you build a typed trace. And with this typed trace, it can trigger the Julia JIT compiler to recompile a new version of the model function. And this new version is more type stable. It's not necessarily 100% type stable, but it's more type stable. And this additional type stability drastically improves the computation efficiency. The final key idea is we want full interoperability between Turing models and the rest of Julia ecosystem. I already mentioned that this is very important because the family of models that users want to use is endless. It is not possible to implement all of those in the PPL itself. And even say we have a list, I'm not sure that's a pleasant job to do. It's just better to let the community to handle that. And for example, all the differential equation libraries are from the SciML system. And this is like probably the best differential equation solver library on the planet. Then some limitations. It is, at the moment, hard to perform more statistical checking on models. So if you want to rule out whether a model has stochastic control flow, it is not easy in dynamic PPL or in Turing. And this is something we can probably learn from the programming language community. Another thing we want but not yet able to do is to extract the conditional dependency structure or the conditional independency structure. This can be done either as a form of static checking or as sort of a runtime checking. Another limitation is sort of on the left-hand side of stochastic statements, we can't use any derivative variables of data. This is implementation limitation. It can be addressed, but at the moment, we haven't done that. Second language I helped implement, which you will see another talk and a poster in the afternoon, is the Bugs language. We essentially re-implemented the Bugs modeling language in Julia from scratch. And I will not go into the details, but I will only say a few key ideas about the Bugs language. It is a very cleverly chosen set of syntax constraints to guarantee a successful mapping from sort of probabilistic program to a probabilistic graphic model. And that probabilistic graphic model allows you to perform very efficient Gibbs sampling. The modeling syntax is very clean and very intuitive. That means it is very communicatable. And that explains the widespread popularity of the Bugs language over the past 3 decades. And interestingly, if you look at the total citations to the Bugs paper, it's still greater than the citations to TensorFlow. Of course, TensorFlow is much more recent, but that's still something interesting. Then the sort of the final core idea for the Bugs language is it is very friendly for compiler optimization and transformation. So the WinBugs implementation supports automated conjugacy detection and automated marginalization. Later implementation also supports distributed Gibbs sampling. And all this can be done without modifying the model implementation, because the model maps to a graph. You can essentially look at the graph to figure out the conditional independence. And with that information, you can run Gibbs sampling in parallel. The caveat with the Bugs language is the syntax is somewhat restricting. And this is something we want to do better in the future. We take the minimal set of syntax constraints learned from the Bugs project or the Bugs language, and then transfer that into a new PPL, like either Turing or some other future PPLs, maybe STEM. Some other challenges or lessons we learned: abstractions are key to decouple model specification and inference algorithm. And different inference algorithms might require different abstractions. So for instance, for gradient-based MCMC algorithms, all you need is the log density function. And then for particle filtering and ABC algorithms, sometimes you need a simulator-based model, sometimes you need a state space model representation. And this abstraction is sort of both model and inference algorithm specific. So if you only work from the programming language side, it is very hard to come up with an inference-friendly abstraction. And even more complicated, the same model can have different abstractions. So that means you need to come up with meta abstractions that will support both, say, log density and the state space model if needed. Some other lessons, interactive modeling and inference workflow are very helpful, but this can take a lot of time to get the design right. So one advantage of working in a high-level language like Julia is the DSL, essentially dynamic PBL, is very transparent to the user. The user can look at the code and quickly come up with a new feature. And these things are harder, not impossible, for sort of standalone languages like Stan or Bugs. You need to have a much wider range of knowledge to be able to add a new feature to Bugs or Stan. Second lesson is interoperability between the programming language and the remaining programming language ecosystem or numerical ecosystem is very important. This allows users to add new modeling families based on, say, differential equations or Gaussian processes. Another lesson is I mentioned in dynamic PBL, the model or the user doesn't specify the type for the model parameters. The way we infer those trace types is the way we run the model once. But this has limitations. So we need better methods for inferring the trace types. We also need a clearer roadmap to guide the problem programming community and also foster collaborations. That's all I want to say, and I would like to thank you for the attention and the entire Turing team. Sorry for the typo.
Yeah, I have a question for you. You mentioned that. Yeah, the microphone. Yeah, thank you. Yeah, hi. Thanks so much for the talk. That was very interesting. So there were a lot of interesting themes that I thought kind of came out in this talk, right? So like one of them is you mentioned that there's challenges in correctness, like with MCMC and so on. And I'm curious kind of what you and your team have done to kind of address this, right? Like what sort of workflows do you have for making sure or helping find these kinds of problems in your inference algorithms like this? And are there case studies or stories that you've encountered that you think would be interesting to share with us about kind of the challenges in correctness in particular that you've encountered? I think everyone here would be very interested to hear more about that.
So yes, that's indeed very important. Because problem-solving languages decouple inference algorithm from the modeling language, that means the MCMC implementation can be treated as just independent algorithms. And we have actually a package called MCMC debugging to test the correctness of all the MCMC algorithms outside the sort of the problem-solving language implementation. You can write a few models. You can write, for example, write the log density for a few models and then just use MCMC debugging package to test the correctness of MCMC algorithms. And MCMC debugging implements some sort of standard ideas from the statistics or MCMC community. There are statistical techniques to test the correctness of your implementation, like the Gewicke testing. Modularity is very helpful. I guess that's the big lesson we've learned. If at the beginning in Turing, the Hamiltonian Monte Carlo algorithm is closely coupled with dynamic PPL. That means if you want to test the correctness of HMC, it's not necessarily easy whether you have a bug from dynamic PPL or from your MCMC implementation. And sometimes a bug from dynamic PPL may even cancel your bug in MCMC. Yeah, go ahead.
Wait for a mic or just shout.
I'll try to go as fast as possible.
Thanks. Thank you for the great talk. I'm curious if in your group's modeling work, there are ever times where you realize that you're going to have to leave the probabilistic programming system and do something by hand, and where those times come up, or if you've found that sort of Turing and Stan have enough features at this point that you rarely need to leave them in this iterative modeling process.
I'm sorry, I'm not sure I got the question correctly. So is your question that sometimes you have to implement new additional modeling families, or just implement the model by hand for certain purposes?
Yeah, either because there's like some performance optimization that the system is not doing, and so you realize that you have to go out and do something manually, or because there's an inference algorithm that you want to try, but it's not something that the system currently automates. Just sort of what sorts of other places does it, I don't know, a lot of times with these domain-specific languages, they can be great if you're within the set of things that they were designed to support, and then as you're iterating, you might discover that you've gone beyond what the designers of the language realized. And so I'm wondering if those settings have come up in your sort of applied ML work, or not so much.
So yes, so the condition deconditioning workflow is actually very useful for that. And that project was some of the original motivations for doing that modularly. Then I mentioned in Turing, the model is completely independent from the inference algorithm. You can just get the log density function of a model and then plug that into any MCMC algorithm you have at hand. You can run the MCMC algorithm from Stan if you want. So that's not really an issue. You can come up with your own MCMC algorithm. Then the computational efficiency is indeed a bigger issue. So sometimes hand-implemented gradient functions or GPU version of your model are just way more efficient than the one generated by the compiler. And the one we have in the MPP is reasonably efficient because it is just a Julia function. So the compiler is essentially generate a Julia function, and you can use all the available profiling tools and benchmarking tools in Julia to understand the performance of the model, like allocation, memory allocation, type instability, extra. And then you just reiterate or update your model to improve that. So there's a package called Turing benchmarking that allow you to identify performance bottlenecks and then improve your model. This is, again, why it is better to work in a high-level language like Python or Julia, because you get the ecosystem, not just the numerical ecosystem, but also the debugging and profiling ecosystem to improve your model.
A question on so your final slide was about the challenges, and the last point was about that we need a roadmap for the programming language community. And in your feeling and experience from machine learning with quite a lot of competence in programming languages, what would be what do you think are the priorities and the main issue, or the point that maybe the programming language community should work more?
Two things that I have in mind. There could be a lot more that we can work together. The first thing is around the Bugs language. Bugs language has been around for a long time. It has some excellent ideas implemented by not machine learning researchers, not by programming language researchers, but by physicists. So the sort of minimal but sufficient set of syntax constraints that will guarantee successful mapping into a graph, I think that's not entirely clear to us. And figuring that out and then sort of implement a set of checks that, for example, guarantee a Stein model can successfully map to a graphical model. That's something clearly useful and something clearly the two communities can work together. Then the second thing is about guidelines for abstractions, because they require knowledge about both inference algorithm and also modeling and also programming language. I think it probably involve intensive discussions, communications between the programming language community and the Bayesian stats and also machine learning community I mean, it probably will take some time to understand the problem, let alone coming up with good abstractions.
Okay, I have one more question as well. And what stood out to me was you mentioned the importance of this unconditioning operation. And yeah, I found it quite interesting because this is the first time I'm hearing about it, even though I've been working for quite a while in probabilistic programming. So I was wondering, could you say a little bit about how that comes up, why it is important, and yeah, how we should think about it? Because like this is a part of a sort of model or submodel API that I've never seen before.
So I can mention two motivations for that. The first is it incurs overhead to create a new model instance, right? So for example, in Stein, if you want to come up with a new data set, you need to recompile your model. You need to write a new model, and then you recompile your model. This incurs overheads. And we want to do this inside MCMC workflow. That means we really need to control the overhead. So if you have a one model and then you condition on certain variables, and then you run some MCMC step, and then you can decondition and run another MCMC step, this actually already gives you a way to implement the GIP sampling. So in GIP sampling, essentially, you are performing condition and decondition during inference. And this means we can implement the GIP sampling as 5 lines of code. So overheads, reducing overheads, control overheads, and also support more advanced MCMC algorithm are the two motivations for the decondition operator. But it can be very useful for debugging as well. You have prior predictive checks. When you flexibly condition and decondition variables, that allow you to understand properties of your inductive bias in the prior.
Great, thank you. Any more questions? Yeah, Sam.
Thanks. So Turing is based on Julia. I get the impression you love Julia, but are there any criticisms or any things you think would make a better basis language for Turing or a language?
So I looked at, when I started the Turing, I looked at several different implementation languages. And back then, Julia was only in 0.2 or 0.3, very early stage. That was a very risky choice. But we thought it's a research project, so it doesn't matter. We had the feeling that Julia solved some MATLAB issues better than Python. We hoped Julia will grow and become more popular, and I think that happened. It's not a perfect language, it has its own issues, but the community is working hard addressing those issues. So for example, in the newest release of Julia, the package loading speed is drastically reduced. That involves some amazing engineering work from the programming language side. I should mention metaprogramming in Julia really make coming up with new ideas on the DSL side easy. We are not compiler experts. If we have to write a new parser and a new compiler for every purposeful modeling syntax, that will take too much time, and I can't do it. So the metaprogramming essentially makes the compiler improvement and development part of the standard programming workflow. That's very convenient, but I'm not sure that's necessary in the long run. Once you come up with the syntax you want, maybe you can do that in other language. But as a working language, Julia is very helpful. Does that answer the question?
Yeah, thanks. Okay. Thanks very much, Hong, for the great talk. So let's thank Hong once more.
Thanks. Should I return the mic?
All right. So next up, we have Zena Tavares from Basis.ai. Zena's been working in probabilistic programming for a while, and I think we're really fortunate now to have Zena working at Basis, which is a startup that is currently trying to develop and continue to grow probabilistic programming for broad applications. And I think it's really exciting that he can come here today and tell us about that. I mean, quite often the sponsors aren't working in exactly the thing that the workshop and kind of the community is trying to work towards. So I think there's a lot of synergy here for us to kind of discuss and explore together. So yeah, I kind of just wanted to give you a brief overview of Zena. So Zena was at MIT for a while. He worked with Josh Tenenbaum and Armando Solar-Lezama. And he's done a lot of really interesting work in causal probabilistic programming languages, and I think we're going to hear a little bit about that today, hopefully. So if you want to talk more to Zena, he's going to be around. There's going to be a social at the end of the workshop today, and I encourage everyone to attend. And in the back, there's some stickers on a table for Basis, which I encourage you guys to check out. They're really nice stickers. All right, great. So with that, I want to turn it over to Zena to tell us about what he and what Basis are up to.